without further ado, since these are recorded and put on YouTube after the presentation, we'll go ahead and get started just in the interest of time. So, hi everybody, I'm Jared Longfox. I'm one of the hosts of this AIAA Space Resources webinar series. Today, we have Dr. Chris Dreyer, Professor of Practice at the Colorado School of Mines with the Center for Space Resources, here to talk about the various work that he and others are doing at Colorado Mines. As always, please punch any questions in the Q&A feature at the bottom of your screen. If you hover your mouse around, you'll see it come up. It'll say Q&A. You just type in your questions now, and we'll get to them at the end of the webinar. But you're not here to see me or hear me talk as usual. So without further ado, Chris, take it away, and thanks in advance for an awesome presentation.
Okay, thanks. Thanks, Jared. Yeah, I'll go to some slides in a moment, and then I'll talk about some things happening here at School of Mines and Space Resources for something like the next 40 minutes, and then we'll go to Q&A. Yeah, I'm Chris Dreyer. I've been a professor at the Colorado School of Mines for quite a while. Most of my time here has been as a research professor. And then a number of years ago, began or helped create a program here that specializes in space resources. That led to this position as a professor of practice. Currently teach and conduct research in various areas of space resources. So with that, I'll go to these slides and tell you a bit more about that. I have to exactly. There we go. And Jared, if you see anything wrong with the screen sharing, let me know.
Will do. It looks good on my side.
Okay. Yeah, so I want to go through a few topics in kind of more recent, current, and highlights of the recent past of activities we've been doing in space resources. So first of all, our program in space resources, site preparation projects, and water electrolysis. We've been doing, we've done recently penetrometers and a few other things. I'll note the School of Mines is actually entering its 150th year of existence, and so it's a big year for us. And we, there's lots of celebrations happening across campus. But what I teach in is the Space Resources program here at the School of Mines. We started this up in 2017. Dr. Aboud Madrid, who's the director of the program, started this up along with assistance from several other more senior faculty on campus. And our idea here is basically the Colorado School of Mines has for its entire existence been about resource exploration on Earth and the transformation of those resources into useful things. And we're extending that into space. Many different people at School of Mines have been active in this field for a long time. And so this, but primarily as a research topic spread across different departments, but beginning in 2017, we created this program to grant degrees in this subject and organize it more into like a field of study. So we offer a non-thesis master's, PhD, and a post-baccalaureate certificate. The program is entirely online. You can take this from wherever you are in the world or whatever. A lot of people are all over the world. We have, I think, more than 20 different countries. People from more than 20 different countries have taken classes in our program. Current enrollment is each, depends on which semester you kind of check this, but is over 120, sometimes 140. And we're at about 30 to 40 graduates per year. We have 4 to 5 core faculty. I say 4 to 5 because we're hiring. There will be something coming out in the fall. We also have a new faculty member joining us in January. We can talk a little more about faculty a little later. We have adjuncts who teach a couple specialized classes. We have at least 8 affiliated faculty, which really is a faculty across campus who are regularly engaged with us in this subject. But they're otherwise primarily in other departments like mechanical engineering, robotics, mineral economics, mining engineering, etc. We've structured this program so it would is if you come from it from science or engineering or economics, law or policy point of view, or many different points of view, you'll get something out of it. And we have students enrolled in our program who are at basically every major aerospace company, both large and small, and NASA centers, international organizations, and startups. So that's our program. It helps kind of explain why it means there were a lot of different activity going on. But I also want to spend more of my time talking about some of our more projects and research-based activities. So this, I'd say this, we teach and do research across the space resources value chain. As you see here, from prospect and explore all the way through mining, processing, manufacturing, and selling a product. And what I've listed here is just a kind of sampling of different activities, tending to be the bigger ones and the most active ones. On the kind of prospecting area, go look at some of these papers I've just listed here. So from several of our PhD students under supervision from different faculty, where it's about like, understanding what resources may be present. Primarily is focused on the moon and this selection. What might be present out there in space? How do we know what might be there? Once you know kind of a general understanding of what a resource is, what might be present, you then want to go and directly run missions that that explore that resource. I've highlighted one. This is a project called Sampler. I'll talk about that in another slide. It's a project with Maxar. We were selected years ago under what was NASA's LSAT-P program. And so we understand it. We'll slate it to be manifested on an upcoming CLIPS mission. A couple other things, we got to move to establish feasibility. This might be fly a piece of hardware that demonstrates a process. An example of that is this tipping point project we had with Oxeon, Oxeon Energy, which also highlight a little bit in the next slide, which demonstrates water electrolysis under lunar-like conditions in a lunar-like feasible single plant. We're then doing a lot of things that are related to mining. So thermal mining is a concept that George Sowers and I, particularly George, kind of championed as a way to extract ice from lunar PSRs. Optical mining is a process that's for asteroid mining that I've been working with TransAstra and Joel Sercel for quite a number of years. Then other things going on, a break the ice competition, which we're partnered with Lunar Outpost, and there's a picture down there of our vehicle. The finals are coming up in just a couple weeks. So we look forward to seeing how that goes, but that's a ice mining NASA competition. Lunabotics is another NASA competition. We have a team of undergrads every year that go to that. It was just concluded. And I haven't heard what the final results are, but well, I know our team competed. They were there. Then we have a couple lusters. Aspect luster is a site preparation luster. So that we're kind of this is more like actually in construction, but it fits into this processing and manufacturing field in terms of the value chain. I actually spend probably most of the time in this talk focused on that. Then we recently, Dr. Cannon has been the PI of the MAGMA molten regolith electrolysis project, partnering with Lunar Resources, and we relatively near the beginning of that one. I also want to highlight we do a lot of SBIRs with different companies, and just as a highlight, there's a small business in Colorado that's doing a lot of different regolith processing methods, and we've had a number of SBIRs partnered with Outward Technologies. But we also do this with a lot of other companies. Some other things we do on the right side, Dr. Sowers particularly is looking at propellant depot concepts, economic studies of the feasibility of use of resources in space. And then we use our graduate project courses as a way to get some ideas beginning, especially ideas that kind of lead to to entries and then into things such as the NASA Big Ideas Challenge, which we've had 3 teams. XHAB's another one. We also had a team years ago in the 3D Printed Habitat Challenge, and we have a team of students who are currently in the Watts on the Moon Challenge. So this is a sampling of various things we're doing. I'm going to spend a little more, go now into a couple slides that highlight individual projects. Really just there's 3 different projects I'll highlight. This is the first one where with Oxeon, we demonstrated solid oxide electrolysis of water. Oxeon is the company that is actually behind the solid oxide stack or processing unit that's part of MOXIE, the ISRU demonstration on the surface of Mars that has converted Martian CO2 into oxygen and carbon monoxide. And solid oxide stacks or electrolysis units are really quite remarkable. There's a lot of different things you can do with them. This little upper right kind of illustrates that, where kind of the right side is the take CO2 and make CO and oxygen. Add a little steam to that and you get syngas. That's hydrogen and carbon monoxide primarily, and oxygen is moved off to the other side of the stack. But you can also put fuel in and produce power, put steam and electricity, and this is where you do water electrolysis. It does have to be run at high temperature, but that gives you an opportunity to use thermodynamics to recuperate a lot of heat that goes into your reactants, that is present in your products. Some of that heat can come from the products, moving heat from the output side to the input side. It gives you some advantages, particularly gets your specific power down lower than any other process that you could conceive of that's similar to this. We demonstrated under 50 kilowatt hour per kilogram of hydrogen output at just under 2 kilograms of hydrogen per day. Theoretically, with some other improvements, we believe it's feasible to get below 40 kilowatt hour per kilogram. Other typical electrolysis systems that run at room temperature or otherwise low temperature are above 50 kilowatt hour per kilogram hydrogen. And so this is a picture of the unit. Here's a publication. There are a couple more that are out there, and then a photo of it installed in our vacuum chamber at Mines, and several members of the team at Mines and Oxeon and some NASA folks. Another project going on, I mentioned Sampler. So it was selected years ago, kind of very early in the CLIPS program, under a program called LSIP-P. It is a robotic arm from Maxar, and then a scoop and penetrometer, as you see on the kind of more early phase conception on the right side. I'm leading the penetrometer. I'm a co-investigator leading the penetrometer and uses of the penetrometer to measure geotechnical properties of the lunar surface. We can also combine that with the scoop to kind of modify the surface and make penetrometer measurements, and we find some really useful things with that. My experience with when I derived some of our experience with operating a penetrometer in this way from something I built and I call the IEP, sort of ISRU experimental probe, that since it's very robotically controlled, we measure forced torque measurements throughout the entire motion with a consistent motion through the soil. And we find we can derive a lot of useful information from the shape of these curves, of the penetrometer curves. Penetrometers are very common in terrestrial practice, and we're simply kind of translating some of that experience to space. Now, Sampler was selected quite some time ago, but it was originally manifested on the Masten Mission 1, but then there was a long hiatus of, I think it's been roughly 2 years, due to Masten's bankruptcy, which people have heard of. That mission will not be flown, and that's my understanding. And we've been told by NASA to anticipate that we're going to be remanifested on a new CLIPS mission as I understand it, it's one that is expected to be the CLIPS provider is expected to be selected later this year. But we're anticipating the restart of this to actually go and fly. The sampler device, the ARM penetrometer, entire thing is actually completely ready to go, waiting to understand which CLIPS provider it's on and how to work out the details of integration. A couple different papers are referenced here. There also is another major one that is coming out from my grad student Ben Thrift and going to be submitted here shortly. So look for that later in the year. Moving on, another big project occurring here, and this one I'll probably spend the remainder of my time in this presentation just on this, is Aspect, which is a NASA Luster-funded project to develop a push-button autonomous real-time motion planning vehicle capable of preparing a lunar surface or landing pad construction. We have and I'm the PI of this, and we have a large team, several different people at Mines. Let's talk about myself, then Andrew Petruska and Neil Dantum in robotics and autonomy. Jamal Rastami is a mining engineering professor, and the test site's going to be built in a location he manages. Dr. Cannon's been advising on simulated lunar surfaces, and George Sowers on infusion. We have a compaction system being developed from Michigan Tech under Paul Vincesante. And the base vehicle that we build off this has been built by Lunar Outpost. There's advising of terrestrial experience and site preparation from Bechtel, and Dr. Phil Abel is our NASA technical officer from NASA Glenn, been with us all the way along, giving us advice and suggestions on how best to do this. So what is it? Well, first of all, what we are to do here is demonstrate a site preparation on terrestrially that is mimicking some conditions in space. The particular luster call we responded to was quite specific about several different things. So many of those are listed here. The most specific and challenging item is that it dictated the rover mass was to be no more than 83 kilograms. The reason for this is that one driving force in your terramechanics, that is how the rover drives around, how much regolith it can push, how much traction your wheels can generate, is its mass, or well, specifically its weight. On Earth, something with 83 kilograms in 1G, of course, will have the same reaction force or the same weight as a vehicle that's 500 kilograms on the moon. So we built something that could be 500 kilograms on the moon, but we've actually lightweighted it to make it 83 kilograms here. So our test with this vehicle really is mimicking a 500 kilogram vehicle on the moon. Roughly same footprint, same wheels, same mechanisms, but things would be added to get it up to 500 kilograms. Also, we're required to do a demonstration of preparation over a 10-meter diameter. This is so that we have enough movement, enough regolith we're moving. We have craters that we have to fill in. There are a number of craters that are very specified, and we have a starting state that's roughly level, that is also then to be a finished state, it's roughly level, and relatively smooth. There's a 2-meter diameter crater that has to be filled in, a number of other craters of different size, rocks of different sizes too, that have to be moved. So 10-meter diameter site is relatively large, and we're building one here. So why are we doing this? Well, why are we doing it this way? The available reaction mass, the weight of the vehicle, is all you have to work with. So due to low lunar gravity, this inherently minimizes the amount of regolith you might move per step. Our approach is we're going to carefully manage cutting and traction forces. We would tend, or as to the extent possible, move only the low density, loose regolith as much as we can, as opposed to cutting into deep and dense regolith. We also feel autonomy should be used in this context because all this would occur before human arrival, preparing a site for, let's say, a human-rated landing vehicle. And we have pursued where we are just imposing that we do use teleoperation. In all likelihood, this is something operating autonomously with periodic human check-in to manage, to see how it's going and manage the process, but not continuous manual operation. This is the vehicle we built. This isn't in CAD. I'll show you it actually driving around in a little bit. On the left is our mass breakdown, and that's how we arrived at the successful mass. It's roughly 2 meters long, a little over a meter wide, and about 1.5 meters tall. What we call the dozer blade is on front. On the front has 2 degrees of freedom. It's really a straight ahead blade that we can raise off the ground and tilt. We have rigid wheels and skid steering. These wheels we've spent a fair amount of time lightweighting the wheels. Lunar Outpost spent a fair amount of time with the vehicle chassis. All the guts and power supplies and brains are under the box, and then there's a base plate that everything's attached to. And the compactor is in the back from Michigan Tech. This might still be an earlier version of it, but it gives you the sense. We'll talk about how that works in a moment. And then there's sensing platforms spread around as well. We're using visual SLAM for localization of the vehicle within the test bed, queuing off different objects within the bed, both surface and rocks and craters. There's a neural network that is built to identify rocks just on images. And we use some of the best state-of-the-art methods to build up this SLAM. A little bit more on that. One of our processes has been that we're using visual identification of rocks through a neural network. So this is what we've done is we've taken a number of rocks in like lunar images, lunar databases to kind of see the texture and features we can see on those rocks. We have others in our test bed. These have been scanned and done the same process. And then we identified that we can identify the rock within a scene. And that's identified within a LiDAR system that identifies and maps the entire surface. We're also using features on the surface to help us do the complete mapping and finish out the SLAM. We're using these Intel RealSense L515 imagers, got both visible light cameras and LiDAR. And these show some of the images of this. Now moving on to kind of high level, how we take data and task planning and integrate it together. This is kind of high level kind of representation that we put together. So we've created a map of the surface. We interrogated to make a decision about whether we have prepared the site or not. Beginning, of course, no. So we move along to task planning. And the task planner selects from a number of different possible options, then passes that to motion planning, which then sets the individual paths. We then execute on it and may have to come back to individual replanning of motion or task. At some later state, it's determined like we're done with completing the assigned task and we go back to resurveying or updating the survey of the site, assess it again. After each task, the site is progressively moved closer and closer to the finished state. Within the ROS planner itself, or the ROS program itself for planning the task, this is from our computer science folks, where what it's subscribed to and lists and watching the luster map and the luster rock positions, takes that to determine the planner and iterates on this a number of times until it's ready to go publish that to the actual vehicle. The luster plan is the plan past the vehicle. In general, for task planning, we believe the these are kind of the questions we're asking ourselves, how to operate this task planning. In general, it would proceed in this little schematic on the bottom to remove rocks first, then remove hills. Hills contain the material that is generally filling the craters. Do those processes, level the surface in general, and then compact and smooth. We do expect some iterations and back and forth on that. In some cases, when filling the craters, the largest crater will remain a hazard to drive in until it's full, and possibly even may need some compaction before it's ready to be driven through. And we're working on this. Individual steps in this process have been executed already, but the full task, the full demonstration is coming up. We also use a few different tools for visualizing the task planning. This is all in the ROS environment. The lower example is an early test with a very coarse grid. So we take the actual representation with a point cloud from SLAM and then change that to a landscape or a workspace that is, each grid point is categorized or given an assignment, an elevation, state like it is a crater or it is not, or a rock is present or not. And the task planner works with that kind of state representation of the surface. And this is just a simple example of the rover avoiding the crater when moving the rock. Now on to regolith manipulation tools. One basic principle I've used is we are moving on a loose regolith. We have a multi-purpose bucket that can do grading, regolith manipulation, grading, and rock removal. There are a number of different kind of steps in the process that we conceive of, such as pushing a rock, lifting a rock, smoothing by moving backwards, and then ripping. That would be ripping the surface is a way to reduce the surface from its dense state to a low density state, which then makes movement easier. We also carefully designed both the bucket and the wheels together by modeling them with some simple classical analytical models, then building test beds and verifying their design. Verifying, of course, the cutting and traction forces we achieve. In the early concepts, we had a much more bucket built for lifting material and carrying it to a new location. As we executed on this, we'd realized that lifting and carrying regolith over the size of the site is really not necessary. And so a more straight ahead, smaller bucket was what we went with. That is really about pushing regolith across the surface. This is from some of our dozer blade performance testing, where we're pushing regolith within a test bed, measuring the pushing force over time. And of course, it builds over time. We're then carefully measuring how much material is in the bucket, how much material has been moved, and we're getting to loads of around 120 newtons. Pushing rocks is also something done. We've primarily looked at rocks that are sitting on the surface, rocks that are partially buried, or for the future iterations of this that might have additional mechanisms. The rocks pushing loads are quite low. So it's really the regolith pushing that's dominant, and these will say it's very important to point this out. The cuts are quite shallow, less than a centimeter. The cutting forces build very rapidly as you go deeper. So careful control of your cutting depth is important. We also have a wheel test rig we built for this. You can see in the upper right video of the wheel. It's self-driven with a motor on the one side. There's load cells in the structure to directly measure the load that it's pulling. It's running across a rail. On that rail, the carriage has resistance and a load from a weight on a pulley in the back. We have direct linear motion from a linear encoder, and then of course rotary encoders on the motors. So we get directly the slip ratio. This is the amount of slip. If you look carefully in the video, you'll see a little bit of slip. The difference between the commanded rotation rate and the basically how much rotation you actually have linear versus how much rotation you have in the wheel. And we're getting a single wheel drawbar pulls up around 200 newtons, and that's sufficient to, on single wheel, this is sufficient to give us everything. Actually, this is for the full vehicle, but this is sufficient to give us everything we need for pushing. They're kind of roughly compatible, and we're continuing to work on our data here, and we expect a publication coming up later in the year. Here's the full system test with our wheels and dozer. This is teleoperated by somebody standing off to the side, and you see mostly some regolith or some rock movement. It is sped up, and you'll see some things like smoothing out the surface, some adjustment of the blade, and more regolith movement and rock movement. So the vehicle's driving around. We're seeing good traction, good regolith movement, and we're close to our full-scale testing. Compaction is coming from Michigan Tech under Paul Vencesante's group. The concept here is to use vibrating pins that are inserted quite deep into the surface. This method really is going for compaction of a surface to significant depth, such as much as 30 centimeters. Reason for 30 centimeters is the natural inner surface is at a low density at the very top, and then progressively becomes denser, reaches about 90% relative density at around 20 centimeters. That's our goal depth. That's our goal relative density, 90%. The bigger crater to be filled in will have a depth of 40-ish centimeters, so it'll have to go in a couple passes. But it is going to be a large depth to compact. It's also very important that there's a loaded plate on top. Some early estimates put the pressure you have to apply on the plate at 100 kilopascals, but it's been found it looks like it can be down at 5.5 kilopascals. But that's a very important step in the process. As the surface compacts, you need to apply pressure to the top to keep it together. Here is a few some of the testing results of single pin actuators. On the left, you'll see this running. The pins being inserted in the surface, then the plate is coming down, and in a moment it'll start vibrating. And there's also a kind of planned motion of vibration with kind of motion of the pin up and down. They found this to be effective in producing compaction. When this is done, we pull that out and we can see a compacted surface. There's been multi-pins done as well, and kind of scans of the surface to get an idea, a measurement of the compaction. And some things we see is that if you start at a very low compaction state, this running now is the vibration unit, which sits above the pin, and it's eccentric weighted gears that are providing vibration. So at a low compaction state, we achieve kind of a moderate compaction. Then in a moderate compaction state, we achieve high compaction close to our 90% goal. There's expectation that with improvements in the kind of cycling of the pin and the vibration frequency, or the duration that we spend vibrating, you might be able to go all the way to high compaction one step, but it might be a two-step process. These are also just fresh off the presses, showing the unit at Michigan Tech that's being finished up. On the video running right now is pin insertion. And on the right is pressure plate motion, I believe. Yeah. And as you can see, decisions had to be made about the number of pins being used here. Ultimately, in this compaction method, number of pins could be varied, more could be added, but just the number actually is limited by the reaction force provided by the vehicle, which again is limited to 83 kilograms. So this compactor is going to be delivered to mines in the next couple weeks. Also occurring, this is actually there's a big effort to build a large lunar test bed, the aspect luster test bed. It's a bit over 100 square meters and is roughly 110 metric tons of regolith in it. It's going to be located at a site called the EMI. Yeah. If you're familiar with Mines campus in Golden, Colorado, kind of some highlights are it's on the Mines campus in kind of a warehouse type space where within the space the major work going on over decades has been kind of rock mechanics in the mining department. And we're taking over a section of space and adding this. We've had a smaller test bed in this in the EMI for years now, and actually the demonstration of the Aspect rover was in that, a smaller test bed. So now we're building this large one where we can do a 10-meter diameter area. And this is a rendering of it, where we also are adding this gantry system that provides following power. We're weight offloading the power essentially. So the rover is plugged in and provides power externally. All communication is wireless. All decision making, all processing is on the vehicle. There's no processing off the vehicle. We're just passively receiving information from the vehicle wirelessly. So technically this is a weight offloading system, but we're really only weight offloading the weight of the cable, but it has a little additional capability. We're making a unique new simulant for this, which at least temporarily I've designated CSM LHT T for test bed. It's a mixture of so it's a Highland simulant, a mixture of anorthosite and basalt. The black line here is our test mixture of anorthosite and basalt. The blue and yellow lines are the global lunar average with 1 sigma, plus and minus 1 sigma. We've also taken this mix and done triaxial tests on it and get a friction angle and cohesion, as you see here. These are reasonable values, and we'll do a similar testing when we have the complete mix ready to go. Anticipate now the test bed will be completed by the end of June, and we'll be running and doing tests in this with the rover in July. We're also looking at this infusion task, which is to take what we're learning here in site preparation and see how can we scale this up. Another direction from the luster solicitation was to look at a 100-meter diameter landing pad. And what would all the ancillary equipment be, and what would a path of flight look like? Well, there's been a overall site preparation system specification written, and we're looking at an operational model to kind of understand site preparation times. With the baseline numbers, we have, most of the distance traveled, which is kilometers worth of travel, is spent moving regolith around to fill craters. Most of the time, though, is spent in compaction. We have since refined this and now can say we find we have a likely path to reduce compaction time significantly, primarily by assessing time spent compacting a crater is long because it's deep, and time spent outside the craters is less time in compaction, a simpler compaction to compact a low depth area where the compaction depth is not significant. And we're now looking at something that's on the order of 2 lunar days to complete site preparation, but that's still preliminary. So finally, some highlights of this. This test bed will be operational by the end of June, and aspect testing will be occurring through the rest of the summer and into the fall. So look for kind of results from us in that time frame. That's it for me for this talk. Thanks everyone for joining us, and let me know if there's any questions. And I'm going to stop share.
Awesome. Thank you, Chris. Great talk. Oh, geez, hold on. Disappeared on my screen. There we go. So in the Q&A, oh, I see Hunter Williams at 3:22 asked, can you talk more about the aspect autonomy scheme? But at 3:25, 3 minutes later, question answered. Thank you.
Oh, it
So
wasn't
perfect.
enough.
Yeah, no, exactly. Hunter, any more questions? Let us know. I will mark these as done. Uh, any other questions ongoing? Punch them into the Q&A if you have them. Um, I guess in the meantime, and you may have said it, what is what is your expected timeline of delivery for Aspect and completed testing?
Uh, Sometime in the fall. One of the things about executing on any of these projects is there's always unexpected delays. We were a bit delayed a couple different ways, but a big one was the details of where we could locate our test bed,
Mhm.
test sites. We had an original plan that fell through when it became clear there are concepts of building a temporary shelter for a test bed was not going to work. And then took some time. We've located the spot in the Earth Mechanics Institute, the
Mhm.
EMI, but it was actually under use and we had to wait for it to become free for us. So that only occurred earlier this year. I'm saying that because we will be going into our third year. Officially, the luster will end next May, but I anticipate we'll really have most of our work done by late fall.
Cool.
So at least the testing, and probably then we'll be writing and reporting on our results in the spring timeframe. So likely doing something. So look for something at maybe some of the major conferences that are next year, and then papers coming out
Perfect.
next year.
Congratulations, you and team. We did have several more pop into the chat. I don't know if they were all actually punched in at once or if there was some issue with my loading, but
Ah,
I'll start from order received on my screen. So James Johnson asks, have any sensitivity analyses been done on visual rock identifying, varying solar illumination angles, and particularly how such systems respond to the low illumination angles of the lunar south pole?
yeah, no, that's a good question. And generally, no. So let me just be honest with that. Yes, we're well aware of the issues of lighting conditions at the South Pole, the low angle of the sun. I would view our sensor selections and some of our methods as being stand-ins for whatever for what might be for what something we can implement here in our test bed today. And in the future, that gets changed to something new and perhaps does directly address that issue. We're not developing a new method that I would say is meant to be implemented on the moon, although it is feasible that the method we've applied under some conditions could work on the moon. Haven't looked at whether low illumination angles would be an issue, or the very deep, very long shadows that occur. So this is a bit of a choice about what are you simulating, and are you simulating everything possible or a subset? And realize we're taking a vehicle and doing several things simultaneously, from moving regolith, compacting, autonomy, moving rocks in a low weight system. So it's about choices of what you're going to simulate and what you're not going to. So the lighting conditions we put off to a later date and expect that there are better that when this flies or something like this derived from this flies, there could be a solution for feature identification that's different, that in that future version is different from what we're using today. So
Well said. Next, Dylan Mikesell asks, what parameters / information do you plan to get from the penetrometer data, and how is it calibrated? For example, on Earth, we do cone penetration testing calibration in different soils within known relative densities and boundary conditions.
yes.
Does that make sense?
Yeah, it does. Yeah. So, yeah, we've been talking a lot about calibrations of of a penetrometer and whether it's feasible. So we've run a lot of our measurements in lunar simulants, a variety of different lunar simulants. So we have that. We know how the penetrometer behaves in lunar simulants, but no matter what we do, the simulants are not the lunar regolith. I think it's important to realize people make the best lunar simulants you can on Earth, but it's still not the real thing. That presents a challenge with the idea of a calibration. We are looking at some methods where in situ you can manipulate the lunar regolith, particularly making a dense lunar regolith in situ and a low density regolith in situ, and running the penetrometer on both of these. And by comparison of these, you can then derive some meaningful, useful information in the geotechnical properties. Essentially a calibration-free approach. What we really need ultimately in time is methods we apply on the moon, like that mimic what we do in the lab or what we do on Earth, which is when you're interested in a soil, you have some question about what is the geotechnical property of this material. You collect the sample, you take it back to a lab, you run triaxial tests, you do a bunch of things. You can produce a penetrometer calibration curve because you're actually working the real thing. And I think the future needs to be that we have tools we deliver to the moon that do this kind of thing in situ. In Sampler, because we have a scoop, some concepts are to make a low density pile, do a penetrometer measurement on that. It's what is the density may be derivable from some measurements of imaging of the size of the pile and density estimations. And then the density estimation comes from actually lots of calibrations of scooping and making piles. And on Earth. And then the natural surface at depth is high density, and this might be a high density version. So we're looking at some calibration-free approaches. It's the simple way of saying it. Ways to operate the penetrometer arm and scoop together on the moon to understand the properties right there.
Cool.
Cool. All right.
No, cool ideas. Next, Samuel Conlon asks, generally, what are some of the major hurdles in designing a system for water splitting in a lunar environment as opposed to a terrestrial one?
Yeah. One thing we found a little surprising was actually the thermal environment and heat loss off the system. Basically, in operating in air, you have continuous heat loss from the system. And that's just a steady load that you have to deal with. You compensate by running more power, if you have heat loss off the system, or you insulate better. While the changing into vacuum, that all changes. And we did find some challenges with, we built for that, and that was one of the reasons we ran it in vacuum. But like an example of this is one time, not exactly sure the reasoning, but we were running in air and we thought, well, to just cool it off a little faster, we put a fan on it, and noticed after just seconds significant changes in its operation because we're just losing heat. We're taking more heat away just with a simple fan blowing on it. And this is because we're boiling water, we're making steam. The steam fed to the electrolyzer needs to be kind of the right condition, and changing that changes everything. Some other things to realize is in any electrolysis system, you don't produce one or both of your product streams are not pure. In the SOXY system, the oxygen line is pure oxygen, but the hydrogen line is always a mixture of hydrogen and steam. I believe in the PEM systems, it's the reverse, but the hydrogen's pure, but the oxygen is humid. Actually not humid, it's liquid. So, but there's always some residual naturally occurring amount of water within both streams. In PEM. In SOXY, one is pure, one is humid, and you need to then extract that and then accept some water. In all likelihood, accepts that some water will be passed on to the condensing unit that will make it cryogenic hydrogen, and that is common. You then need some system that then it takes out the remaining water. So those are just some other natural kind of occurring parameters around producing hydrogen and oxygen, is that the product streams are not pure, caveat, oxygen in SOXY is pure, and you have to kind of treat those properly so that they pass on to the next system, and that system can handle the amount of residual water that's present. Okay.
Perfect. Next, Brian Case asked, do you have, I think we already discussed this, do you have future plans for lighting testing in the lab to test under navigation under realistic conditions?
Okay, yeah. So under Aspect, I don't have plans directly as part of Aspect. But look, actually, we're building this big test bed. We're doing Aspect for what I think is, we'll run this as often as we can, and we may achieve all of our goals for the Aspect project by within sometime in the fall. But I anticipate it's a test site, it's a test bed that we're going to be using for other things. We've already written some proposals proposing its use, and in doing so, we will incrementally add improvements to the system, and lighting is definitely one. So we don't have a unique lunar-like polar lighting system right now, but yes, it's definitely on a list of upgrades that we would apply in the future.
Cool. Last one in the Q&A. If anyone has any, punch them in. I do have a question, but you guys take priority. So anyway, Quinn Morley asks, is the vibration compaction idea using the small rods inspired by the method used for building foundations in Venice, Italy, using thousands of poles driven into the mud?
I don't believe it's inspired from that example directly, but it is inspired from terrestrial construction practices. I think Paul Vencesantes mentioned that it's more inspired by the kind of land reclamation, is that the right term? But levee building in the Netherlands, where sand is brought up and then kind of a ground is created. The seawall is created because most of Netherlands land is below sea level, and there are methods used there to compact the sand that's brought up that are similar to this, and of long poles pounded into the sand, vibrated, and kind of then this makes dense surface at great depth left behind. So yeah, it is inspired from some terrestrial methods. Not that one particularly, as I understand, it's more of a derived from the Netherlands.
Cool.
Right.
Okay. Makes sense. Considering the creator of that system.
Yeah, yeah, yeah.
Anyhow, so we do have just a couple minutes. I do want to sneak in one question.
Yeah.
What was the most unexpected yet significant challenge you came across while building Aspect?
Uh, um, there's been several. I would feel compelled to begin with just the politics of building a 100 square meter test site at a university campus, and
Yeah.
finding the space, finding people who will finding a way to do it that just the roadblock won't be thrown up in front of you, and finding a way around the roadblocks. I know at UCF, you guys recently built a similar test site. I don't know if you
Uh,
had a similar uh, discussions with campus folks where, that jeopardize the building of your site, but we've had various needs to kind of navigate a way around and find a way to do this that everyone's satisfied with, that doesn't require making fundamental change to a building on campus, which then invokes a lot of time, a lot of additional cost. So
yeah. No, and the logistics of that are insane. I won't speak for any of those who led that effort at UCF, but yeah, it was absolutely ridiculous. So cheers to you guys for getting through so
um,
far and actually finding a place. That's the biggest hurdle.
yeah, yeah. What and it's just to bring up one other. Well, you did ask for the one, but maybe I'll get
No,
the
please.
three in a second. Just because that one's more it's less technical, and the second one is more technical. And that is the weight offloading turned out to be more challenging than we expected. It really isn't, 83 kilograms. Actually, I mentioned Lunabotics. Those vehicles are typically that, but we have a different task, and we are a little bigger. We actually began looking at it like you're not just running a competition like Lunabotics for 10 minutes. We need to run for days, most likely. And actually, we thought about putting battery. We thought initially we could put batteries on, and we could have, but we would have been recharging the vehicle very often, so often that we'd spend just a lot of time in that charging or getting out there to go recharge it, and it would have disrupted our testing, and I made the test less lunar-like, I think, in fact. So actually, I mentioned the luster we responded to had very specific rules. It actually said no. I think it said it must be battery powered. So we asked for permission to go to tethered power, and that then freed up much more space for mass. We still was a bit more challenging to hit the mass target we were aiming for. Um, Now, I say related to this in getting to low mass, that's part of the lunar simulation, because then the rover has a weight that's similar to what it could have on the moon, in spite of it being in 1G. However, the regolith we're working with has the bulk density of lunar regolith. It is the same, very similar bulk density. So it's not weight offloaded at all. So we're pushing around regolith that is 6 times too heavy. Now, some of the pushing force comes from shearing, kind of cutting into the regolith, and that shearing force, that's not going to be highly driven by the gravity field it's in, but the weight does. And so one other thing is realizing that it's only partially a simulation, because a weight offloaded regolith is in such a large quantity is a I would call it infeasible, but maybe somebody could come up with a clever way of doing it, but 100 square meters is pretty big. So I know that the weight challenge was a bigger one than I anticipated. I knew it would be a bit of a challenge, but it was a bigger one that then when we got the permission to wait or move the power off, go tethered power, that freed up a lot of that made it possible really to do it.
Well, I'm glad the program was flexible, and yeah, I can't imagine the challenges of actually having to run that test. But anyway, we are at the top, actually a minute over our hour. So Chris, thank you very, very much for giving your time and expertise, answering questions. It was an awesome presentation. Um, the
Great.
rest of you, thank you for attend. Oh, go ahead.
So I'm sorry, you go ahead. I'll thank you.
Everybody else, thank you for attending. Stay tuned for next month. And Chris?
Yeah, and I'd like to thank everyone for joining and attending. And if you have any other questions, please feel free to contact me. I'll try to reply in a timely way. But um, yeah, thanks for joining.
All right. Cheers, everybody. See you soon.
Okay, bye.